Hello, everyone, and welcome to today's live stream with the Wolfram Institute. We're doing some live science today with Nick, peeling the quantum onion. Nick, take it away.
I'm excited.
Yeah. So you can see my screen, right? Okay.
Yeah,
So this is like the motivation for this, I don't know, talk or conversation is just that has basically to serve some kind of introduction to quantum computation from the visual motivation, or maybe just trying to explain all the visual components of the following picture, right? This is like you already whoever already familiar with the quantum computation, you already see the block sphere in there, which is a representation, graphical representation, geometric representation of a qubit, which is a two-dimensional quantum state, right? But there's like much more components to that block sphere that one can identify and then try to explain. And it's like, and you can even identify a bunch of like platonic solids in there. So there's like, you already can see that there's besides the sphere, there's some tetrahedron in there, a cube, and an octahedron, right? And they all have some kind of meaning that you can decipher from the quantum theory. And I have like a nice, like a little motivation. And there's like a nice manipulate that you can peel it so that we can go one by one, explaining piece by piece what those geometric objects are, even at those points. So there's like a three platonic solids, block sphere, and also octahedron, which is green, this cube, and this octahedron, which we can start with this one, right?
Should we just mention the block sphere, because you mentioned something there. I think most people are familiar with the block sphere if you're doing quantum studies, and it's a 3D object, right, representing a two-dimensional qubit. Is that the right way to describe it?
Yeah, this is like a block sphere on its own. It's like every quantum state, right? Every like randoms or pure or whatever, any quantum states, which is in traditional form in textbooks is represented in traditional form is just some kits like and complex amplitudes. That's how you can encode a quantum state or qubit. But it can also be converted, all those quantum amplitudes, a pair of those can be converted to a 3D vector, which is a block vector. And on the block plot, it's just an arrow, right? So that zero state is the north pole, one state is the south pole, and all other three projective bases are in the corresponding axis of that 3D plot.
and
Right? So
so these two complex numbers on the kets, right? The amplitude squared sums to 1.
Yes. So they always normalize if it's a pure state.
Mm-hmm.
So amplitudes list are those complex numbers. It's just for random pure. If you norm, if you compute the norm, it's going to be 1. Norm is just, as you said, is just absolute squared, right? And total them. So they normalized. So those behave like Born probabilities. You square the complex number and square it, right? But there's also, so that basically means that it's a pure state and its arrow or block vector is a size 1 and it points on the point on the sphere, not in the bulk of the sphere. If it's a mixed state instead, this is, so if you take the mixed one, right now, instead of pairs of quantum amplitudes, it has to be represented by 4 numbers, which is not the degree of freedom. It's essentially you have to represent it with the density matrix. Right now it's a matrix, so it's 2 by 2, right? But it's a okay. Let me chop it. So it's a real numbers on the diagonal and some complex number and its conjugate. So it's like the same number when the sign of the imaginary component is flipped. Those are diagonals, which are called coherences, right? So now the probabilities are on the diagonal. So this is the, without any squaring, those diagonal elements, now the real numbers that represent the probabilities. So, and if you plot this state on the block plot, now it's going to be some, well, in this case, very tiny arrow. So mixed state now is not pointing to a sphere. It's not norm 1, right? If you compute the norm of that particular one, or norm is a little bit different. If you compute, how we would call it? Well, essentially just, I don't know even how code, just norm of the underlying block vector. It's less than 1, right? So any mixed state is an arrow pointing in the bulk of the block sphere. So that's the representation. I can like explain maybe how it's computed from those amplitudes if you wish to, but it's related to Pauli matrices. It's like if you just take, it's very pretty simple, but I know.
This is the plot of a mixed. Forgive my ignorance. So
Yeah.
with the pure state up top, right? So you had these two complex numbers, and when you take each complex number, you take the absolute value of it. So it's complex norm, I guess. They have this norm and that norm, or this norm squared and that norm squared as real numbers. Then, and the sum of those two squares is equal to 1.
Yeah.
Right. So that means that it's like the pure state is some element of C2, right? Complex 2 space.
Yeah, projective complex plane. I think, because you also don't care about the phase, right? You can, I think I even have this option.
Right,
I
right.
don't use
That was the other thing. Like, is there a relationship on the phases of those two parts?
Yeah, I think I can enable this representation, maybe show flag. Yeah, it's like you can essentially also somehow show the phase of that particular. Of course, it's ambiguous what
Okay.
actually constitutes a phase, right? But you can prescribe some kind of scheme to extract the phase, the common phase of any quantum states, which is represented by two complex numbers. You can divide it by some number, maybe divided by the first number, right? But one of those complex numbers, and define the phase like that. And now you can, instead of an arrow,
you can divide it by something which normalizes the phase for one of them, I guess. But in any case, so this, all right, so that's because two complex numbers with norm squared, I mean, basically you're looking at S3 inside of C2, right?
Yeah.
But then if you mod out by phase, and you're just basically doing the hope projection, right,
Yeah,
down to the base space of S2. Is that accurate? James,
somewhat.
Is that geometry that you're speaking there, Dugan?
Yeah.
Okay.
Right. So that basically it's you have two complex numbers, so that's 4 real variables keeping track of the real and imaginary components of two complex numbers, right? And then if you're stipulating that the norm squared on that 4-dimensional vector is unital, is 1, then you're restricting to a 3-dimensional sphere inside of R4. And if you're modding out by phase, then you're doing a algebraic or a topological projection, basically, from S3 down to S2.
Yeah.
And this is what's described in the Hope vibration, HOPF.
Right. Yeah. There are many geometric representations of the same thing. It's like you can use this one single number. If the state is pure, you can represent it by a single complex number. So we can put it on the complex plane with infinity. So some states like South Pole or North Pole can represent the point at infinity on the complex plane and all that, right?
Mm-hmm.
But the block sphere is just, it's more common. You can actually visualize any point just on the sphere without going into infinity. So that's fine.
Right.
Yeah.
I mean, that's a different thing, is the stereographic projection of complex plane adjoint infinity wrapped up onto the sphere. But I mean, it's a different thing at least for me to think about if it's if we're dealing with the Hope map from S3.
Is there code that you can write to show what you're talking about, Dugan? Like, is there the S3 C2 what?
Well, hope projection maybe is not very trivial to code, right? In live. I kind of seen the formula. There's like just like mathematical formula. I can compute all those circles, right?
Mm-hmm.
So it's not built in yet. We don't have a built-in.
No, I don't. Yeah. We need some nice visualization for the hope vibration, I think.
Okay, that's
just
a project for next time.
With one line, so that you don't have to think too much.
Very cool.
Yeah.
Okay, I had a quick question. So, can you just explain what those little bracket notation actually means, like with the pipe and then the arrow? Yeah.
I think this is very simple. It's like each of those kits is essentially some element, which is like well, technically it's like an element of the vector space. And in this framework, for example, it really means that every state has a basis, right? So and each basis in this case it's a very simple computational basis. It essentially means that this ket 0 and ket 1 just have unit vectors. It's like 1, 0, or 0, 1. So that's the representation of those particular elements, and we just only scaling them by complex numbers. So we have vector representation of size 2 for each of those elements, and we just scaling them with complex numbers, and that's how the whole quantum state is represented. It's just you pick the representations, right? If you, for example, take the same state and convert it to a different basis like X basis, now it's in X basis, right? And it has a different representation, and the state in this particular basis looks different. Right now, the complex numbers are different from this one, even though it's the same state. Right, you can take this one, ask
Yeah,
whether
hold
they
on. Sorry. All right. This is in an association data object.
no, it's a
Well,
traditional
the row
form looks
basis.
like
I mean, or call it peer row. Anyway, the
I
out
can switch.
331 on the line above.
Yeah, this one.
Is that
So
an
basically,
association?
it's a well. I show it as an association, so that you can easily show it. But I switch back and forth from traditional form and the normal form. Normal form is just an object, which is called quantum basis, and it has those representations of each of those elements somehow embedded in it, right? If you want its input form, it like looks more complicated.
Okay,
right?
so it is an association. So associations use the
Association
the
is
thing.
like
All right, yeah. So those orange characters are confusing
Orange.
with the bracket and the ket notations also. I
Oh, yeah,
I forget what
when
we
they-
call it, like a triangle or like a bar and a.
Yeah.
I don't
So
know.
those.
That's a Wolfram language thing, right?
That's
Yeah.
a Wolfram language thing. So it's using those ligatures.
This is the
Right. That's
It's
the
confusing when
syntax
you write.
for inputting an association into Mathematica.
Yeah.
So that's
right. Yeah.
not to be confused with the kets
Kits.
and it's not shown
So
here, but the
essentially,
bras.
like maybe instead of looking at the association, essentially basis consists of names
Yeah.
and corresponding elements,
Mhm.
which is just some vectors, list of vectors. So instead of just actually associating them with an arrow and some weird brackets, okay, they just get them separately.
Okay. Now,
Got
just
it.
like in a vector space, you take these vectors and you
Yeah.
have linear combinations of them where you assign coefficients to these basis elements, these basis
Yeah,
vectors,
exactly.
and so here we're using complex linear or complex numbers as our coefficients for this thing.
Yeah, it's essentially we have a complex field, right? Vector field of a complex field, how's it called? Whatever. Yeah, we get it. So a state can be represented in different bases, and that's what are those kets represent. Those are
Now,
just elements of
the 0 and the 1, those are different qubits, different. Why are they different basis elements?
we have
It's
a two-dimensional complex. So you have to make, because it's two, you have to have two elements, right? Orthogonal, ideally. So that's 1, 0, 0, 1. Those are orthogonal elements, and they represent 0 and 1.
But that's one qubit with two.
Well, it's a basis for the qubit, right? It's how
The
you
basis.
choose those two elements, 0 and 1, and then you can, using those two elements of the vector space, you can represent every qubit by assigning different coefficients. Using complex.
Are these two different? This describes one qubit.
Yeah.
Okay,
Can
so
you have-
and so there'd
Can
be
you have
like
three
what-
elements? Or no?
Hold on. Okay, try to formulate your question clearly. It's like, so a qubit have a list of amplitudes, right? Those are these complex numbers. those are like coefficients for some basis elements, right? We can choose any basis. It can be even be non-orthogonal. In this case, we're just picking two elements that have this specific representation. So it's like a coefficient. So this is the complex coefficients. We choose the most simple ones, 1, 0, 0, 1. It's like an identity matrix. We pick those elements, and then we can represent in this basis every other quantum states. We just multiply these vectors by complex numbers, and then that's how we encode arbitrary quantum state or qubit if it's two-dimensional.
Is this describing like the spin state of one electron or one atom?
No, it's like an internal state of a spin 1/2 particle, a fermion, right? A
Okay.
single one.
So a
qubit
fermion.
and a single fermion are equivalent. It's like if you have multiple of them, then there's some technicalities about the tensor product. But yeah, essentially, qubit is equivalent to a spin 1/2 particle.
Okay, so each spin 1/2 particle, each one of these fermions needs a 0 and a 1 of its own, or it's a two-dimensional type of thing, or CP2.
It's a two-dimensional in a sense of complex amplitudes, right? But it depends how you prescribe it. The point of geometry is when you look at the geometry, it's very simple. If you have a block sphere, you just pick a point, and those represents the whole space of all possible qubits, right? It's a space of all qubits. So any point on a sphere or inside of it is arbitrary, can represent arbitrary qubit, right? If it's on a sphere, on the surface of it, then it's a pure state, right? Then it can be represented by just two complex amplitudes. If it's inside of it, then you have to use a density matrix. But the point is that because it's three-dimensional, it's enough to have 3 degrees of freedom. So it has a 3 degrees of freedom. So the 3 real numbers are required to represent it like completely any point in the sphere, inside or outside, right? But if it's pure, only like longitude and latitude only can prescribe the pure state.
Well, that's 2 degrees of freedom on the surface of a sphere.
Yeah, it's enough.
It's pure.
So that's why you can project it on a complex plane. So you can a pure state can be projected to a complex plane and represented by a point there as on a two-dimensional plane instead of a sphere.
Right.
All right. So I got a quick question here. So if we look at this block sphere, there's a 0, 1, which we mentioned is the basis, and then you've got the plus, minus, and LR. Are those optional as well, or for any qubit basis, is there always that plus, minus, LR?
Oh, that's just a different basis, right? You can pick any two. Oh, you pick an axis, right? Going through a center. That can be that would be your arbitrary choice of basis, a projective basis. Because in the block sphere, the axis represents confusingly an orthogonal basis, right? This like actually the 0 and 1 would be orthogonal elements, right? Even though they are actually in this 3D geometry, they are not orthogonal. Those are like correlated to the spin, and when those are like 4 pi degree rotation and all that. But yeah, this is just another sets of bases that you can choose. This is like the computational basis of z-axis, right? X-axis and y-axis. Those are the natural axes in 3D. So we can choose them as a basis, like we did here, right? We chose X basis, which are plus and minus here on the blocks.
Okay, so you chose that different existing axis. Okay.
So that same
cool. So
that same point with that orientation, I guess, can be read off in any number of axes. Bases.
Well, a single axis, but it can be any axis, right? Axis. Right. Yeah, it's gonna be right.
Okay, so most people, when they start talking about qubits, this is the original. This is like the first thing they exposed to. But what you're saying is this is actually just one of the layers of a potential onion of interesting things to explore here, right?
Yeah. If you start from a conventional quantum computation, this is like maybe constituted as a first layer, right? That's the first thing, a geometric thing you learn about qubits. It's a block sphere. There's an arrow representing any arbitrary quantum state, right? Maybe it's a flag. There's a basis as axis and all that, right? Maybe you also learn that if you do the projective measurement, then, for example, if this is your quantum state, and you measure in this basis, because we usually talk about measurement in some basis, right? You can measure your electron moving like horizontally, vertically. This is like, or photon, whatever is your physical manifestation of the qubit, right? You can measure it in some particular axis, right? The spin of the photon, and that's actually constitutes a projection. So, for example, in order to extract the probability, you just take this vector and project it on this axis. That's how decoherence happens and all that, and it's like how the quantum state becomes probabilities of measurement that we experience in the lab. Okay, but should we go to the next layer?
Yeah, let's go. Can we also maybe go to 200 zoom, because there's not long lines of code, so it's better to get like a full zoom on our onion. Yeah, there we go. Cool.
Okay, let's just peel. Well, actually, we don't peeling because we're not starting from the outer layer. So the tetrahedron one, I think maybe the natural one is the next, because tetrahedron represents the probability space. So we're kind of coming from a completely other direction to the same mathematics, right? I already had some blog post I written some time ago. I think this one. That's kind of okay. Let me make this one 200, which kind of explains the tetrahedron relationship to probability very quickly, right? So if you start from simple coin, which is just a two-valued random variable, right? So it's represented by a two-dimensional probability vector, right? And the space of all probabilities, so the space of all unfair coins, and can be represented by a line.
A coin?
A coin.
Right,
Yeah,
so it has like heads and tails. That's a discrete set.
Yeah, so it has a discrete set of two values, right? But the coin can be unfair or fair. The fair coin usually lands heads or tails with 50-50% chance, right? But there can be an arbitrary unfair coin, and with 75, 25, 100 to 0, those kind of chances, right?
So
and
we're talking about the probabilities here. We're not talking about the actual head or tail. We're talking about the probabilities of it landing on either one at any spin.
The space of biases, or the fairness of a coin is this line interval, one dimension.
Yeah, exactly. So kind of you basically, now the space of all possible coins, all the possible probabilities one can assign to an unfair coin is just a line, right? It's just one-dimensional line. And it's called a simplex. It's just a two-dimensional simplex. You can simply write it as show the same kind of thing, either like that. Right? Maybe you put some axis on it. Right, right. So now, like every point on that line would encode the probabilities for a coin. A fair coin 50-50 is just right in the middle, and the extremes of landing always landing on heads or tails are there.
Right. So the in this case, you could say that the for a coin, you could have its probability for heads being one axis and its probability for tails being the other axis, and they're linked in the fact that the probability for tails is always 1 minus the probability for heads.
Yeah,
so if you plot the line y equals 1 minus x, you get this. And then if you confine it to the probabilities have to be between 0 and 1 always, then you're looking at this line segment of possible biases for a coin. Plotted
essentially, line segment shows also all the points, two-dimensional points with the valid probabilities, right? It can be like 50-50 is 0.5, right? It's here. Like 25%, 75% is here, right? So it just shows all the valid probability distribution that sum up to 1, right? And a simplex is just a geometrical object generalized to arbitrary dimension that represents it, right? So the two-dimensional simplex is representing a one-dimensional object. Object is which is the line. So there's actually, even though we plot it by default on a two-dimensional plane, it's actually a one-dimensional object. So we can kind of rotate it and think of it as a number line. So because there's only 1 degree of freedom, because another one is determined by just subtracting it from 1 in order to normalization to hold. But when you generalize it in the higher dimensions, like 3 dimensions, right now, the simplex is a triangle, right? Now you can represent it again. Now you have to plot it in 3 dimensions. right? Now
Mm.
there are 3 points, right? There are some three possible deterministic values. Maybe it's some
Okay,
kind
so
of
now we're talking about like something with 3 values. Like, okay,
Yeah.
going away from the coin analogy. If you imagine like a football, but the football has like 3 flat faces on it. So you drop the football and it lands on like one of the faces down.
very weird football. Yeah.
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 But I mean, any sort of, I mean, I'm trying to think of like there's no standard like Dungeons and Dragons die that has 3 sides to it.
Yeah. Well, maybe
Right.
you can like imagine that you have a cylinder with a triangular base, right? And it's just
Yeah.
very long, so that there's like very small chance of actually landing on the base, right?
Right. So
It's
if you had a triangular prism with pointy ends such that it can't land on the pointy ends and it has to land on one of the triangular facets.
yeah.
Then
If you want to imagine those kind of objects that you're actually throwing, yes.
Mhm. Okay, so and then we're looking at, okay, well, what's the possible biases for that kind of thing, that kind of setup?
Yeah.
And so it would be, you could think of it in a 3-dimensional context. You could say, okay, well, there's one axis for landing on 1, and one axis for landing on 2, and one axis for landing on 3, and the probability for a specific one of these objects for landing on those values would be the space of x plus y plus z equals 1. So that's a
Yeah, so that makes total sense in 2D space, but how does that now work in 3D? Why would there be a
well, I mean
three-dimensional?
So essentially, we get the same points, right? Before we took these points for our extremal points, right? Just 1, 0, and a 0, 1. Right now it's 3 points, but in 3D space, again, it's just those corners of the triangle, and we just fill
Okay.
the space.
So that would be the full 3D space, but it would only exist on that plane, somewhere on that plane.
Yeah. I mean,
Yeah, any point on this triangle represents a valid probability distribution of these 3 values. So if you sum up those probabilities, you get 1. Essentially,
But there would be, so there would also be invalid probabilities. What would an invalid probability represent?
well, invalid
something
probability is
where
any point
like x
outside
plus y plus z is not equal to 1. I mean, so
No, but I mean, like in reality, what does it represent? Like if you have a probability of all of them being 1, that's invalid. But
right.
what is that?
Well, it's kind of, well, this post was kind of about it a little bit, right? If you want to remind us, I was kind of, where's the picture with the Pikachu, your favorite guy?
Yeah, there
right?
we go.
Look, it's like essentially invalid probabilities is kind of can naturally or not unnaturally, if you wish, can arise when you just pick a bad basis, right? Because when you have this probability space and you use your basis as those extremal points, then you can represent any coin, unfair coin, between them naturally with a probability distribution. But if you pick some basis like this is your basis now is like different unfair coins. Those would serve as a basis. If you ask what would be this unfair coin in terms of this basis, you just by linear algebra would produce some unnatural probability distribution with negative numbers and numbers greater than 1, right?
In terms of the blue basis there, I mean, in terms of that point.
Well, in those 2 extremal points, right? Instead of those 1, 0, 1, and 1, 0, you choose those 2 points instead. Right?
Okay.
It's kind of just shrinking a little bit your space of possibilities, right? And if you ask some question, because always the basis is, you can think of the basis as some kind of test that you run, statistical test that you run on the object, like on the unfair coin, right? You always ask it some question whether it's this or this, like is it
so that
blue or
that
yellow?
that might represent something where the answer depends on who's asking the question. So if I want to win every time, you can flip the coin, but regardless of the outcome, I can arbitrarily choose the result I want later. Something like that.
Yeah, well, I didn't
I mean,
get it.
I'll
It's like changing the rules of the game. In other words, like saying heads or tails, but then you can change what heads and tails, the definition of heads and tails after the coin is flipped.
I mean, this is changing the definition of always. Probability 1. It's saying like, what if probability 1 was like over by 0.7 here for the orange. I mean,
Yeah, well, it's hard to imagine the actual physical situation of throwing coins. You can't really compare a single outcome of a coin cost to a blue unfair coin, or maybe you can just toss them like together, something like that. But you also do some post selection by always picking when this one lands actually on the blue one.
Exactly. Yeah.
So you have to do something weird, but you can do it. You can use it as a test. It's going to be a very weird test. It doesn't work 100% of the time because you have to post select and all that. But you can technically do it. And if you do it,
yeah, it's possible. Yeah.
I don't know. I mean,
Let's get back to
Shenanigans
the
opened up
onion,
a hotline recently. I'm going to call them. I'm going to call them.
Okay, so we haven't even got through the first layer of the onion yet. So let's get
Yeah,
back
we're-
to the onion.
yeah, let's speed it up a little bit. So yeah, we can kind of figure out how it works in for 3D, right? To have a ternary plot. And now, and the next step is to go to 4-dimensional case, which can be represented directly, but because we showed this projection, that you always rotate this simplex and just throw away some of the coordinate, you can imagine that it's just a 4-dimensional simplex, some arbitrary like tetrahedron, projected to 3D is just a tetrahedron. So probability space for 4-dimensional probability distributions is essentially can be represented by 3-dimensional tetrahedron, right? So and that's what we're showing as a layer in our Qubit onion around the sphere, right? So now we essentially kind of trying to construct a probability space. So instead of looking at the quantum state at the qubit as some quantum object, we just look at any point that represents a probability distribution. And there is a natural way, mathematical way of actually turning qubit into a valid probability distribution. So it's a subset. So it forms a subset of all probability distribution. That's why it's nicely embedded in the tetrahedron, like touching it with only 4 points, right?
Oh, so if you spin it around, you can see how it touches is important. Okay.
Yeah. So essentially, there is a mathematical procedure of turning any quantum state with those complex amplitudes to a 4-dimensional probability vector, right? Living inside this probability space, which is a tetrahedron. So, and then the mathematical procedure for it, we have like we just call it a quantum phase. Oh, actually, we have a row here, right? We just can call it quasi. No, we just do the quantum phase space. Quantum phase space transform. And we have like a special basis, which is also conveniently called tetrahedron, which in this basis, it becomes 4-dimensional, but now its amplitudes is just 4 numbers representing those probabilities. So the number, essentially the number in this 4-dimensional space of probabilities, of which this is the projection. It's just looking at the projection. So now we have like some mathematical way. I'm not going to explain in detail how it's done, but just turning any point on a block sphere into a 4-dimensional vector. So this is always going to be positive numbers summing up to 1, between 0 and 1. So no problem, right? So and it's a subset because any quantum state is a probability distribution, but not any probability distribution is a valid quantum state, right? That's why there's technically some points outside of the block sphere.
So the tetrahedron here represents the space of anything that
Anything,
could happen.
4-dimensional. Yeah, it's like there's some abstract basis. Now we have dealing with the 4-dimensional basis, right? This is those represent the vertices of a tetrahedron. So it's just 4 points of that simplex, and we kind of testing our quantum states using those points, right? Now our test function, where those extremal points of the simplex, now testing the quantum state. Essentially, this constitutes a measurement. It's some kind of positive operator valued measurement or whatever. That essentially testing the qubit and extracting the probabilities. And the transformation is 1-to-1, right? It's like you can go back and forth. So it's just mathematically equivalent. Either you work with density matrices and complex amplitudes, or you work with these 4-dimensional probability vectors, right? If you wish. Right. So now,
and is it always referenced from the center, like in terms of the length of the arrow, it's coming from some central point inside the very middle of this space.
Okay, maybe I want. It's beneficial to actually describe this some special point. So there is a special state called uniform mixture, right? Which is a mixed state. It's a completely mixed state that essentially 50-50 chance of measuring 0, 1, classically.
Mm,
Right.
mm,
So that represents the pure center of the block sphere.
mm.
Right?
Nothing
So it's a
weird there.
complete,
That's just that.
yeah,
Yeah.
it's a complete noise. It's like you just get one or another with equal probability, and it's like different from the pure state plus, which is kind of important, right? Because pure state plus, if you look at the quantum amplitudes and square them, you also get 50-50 chance of measuring either 0 or 1, right? But this is the point on the North Pole, which is the not the North Pole, but some kind of equator point. So if you measure this point in this basis, it's kind of completely orthogonal to that. So this point plus projects on this 0, 1 axis completely in the middle. Or in fact, any point on the equator or in the disk equator projects to that point. So in a way, if you measure it in this basis, you always get 50-50. But this point
So it depends on the
in the middle is
measurements.
yeah.
So your
the
basis
point in
of
the middle,
measurements can collapse the probabilities back to a 50-50.
yeah, that's what it does. It's like projective measurements turns your quantum states, projects it somewhere into the axis, and it becomes mixed. So unless you measure exactly this state or this state, right? That's the only points on a sphere that projects to itself. Any other points actually projects into the bulk. So it becomes mixed. And in the extremal case, it projects to the center. So it becomes a completely mixed one. So it's like 50% noise.
So
those are
and
kind of
is that
different
like, you have this fermion, this electron, you're scooting, or some sort of particle, and you're scooting it through a vertically aligned magnetic field, right? And depending
Polarizer
on
or
its
something.
spin axis, like if the spin axis happens to be horizontal and it goes through this vertical field, then it's either gonna like turn that way and align and go down, or like turn the other way and go up, and it's like a 50-50 split.
First of all, it's not even correct to assign a proper orientation of the spin for the qubit itself. You can assign it to the basis because you know in which basis you measure it, but you don't know. There's like no point on the block sphere that tells you exactly which orientation it is. Well,
Yeah, so I was bringing it
only a
back
single point.
to the classic Stern-Gerlach, where it's like you have these aligned these fields, these magnetic fields, and like either it's spin up or spin down or something like that.
Yeah.
But I don't know how this relates to that, if at all.
Well, it simply relates when you set up this non-uniform magnetic field, right? And you measure your internal representation of the electron, the spin, right? Like any point when we don't know this quantum state, right? That's what we are measuring. It can be arbitrary, for example, arbitrary block vector. But when you measure it, as a result, it projects effectively on the axis, like z-axis usually, and that's how you measure the probabilities. If you repeat this experiment multiple times.
Got it.
Of course.
Okay, cool.
All right, so yeah, and that also the center of the block sphere in the probability space is going to be just uniform. So if you just do the same procedure and turn it into a tetrahedron basis, ask for its amplitudes, it's going to be just a equal chance because it's just right in the middle. So the probability of completely uniform distribution, again, exactly in the middle. So that's why you get the uniform distribution there. If you test it with these 4 bases corresponding to vertices of a tetrahedron. Right. So that's the probability space layer, I guess. But there's some dedicated points in there, which I kind of want to explain.
Is the tetrahedron like a selection of those cube points, like the red and the teal? They're just scaled up, or is this actually like a volume of values that's contains in it? I guess it's
no. Don't look at those points yet. That's the thing. The next thing I want to explain. This is just those T1, T2, T3, not labeled, right? Those corresponds to the bases in this probability space, right? Those are the actual states, right? You can actually, there's
Well,
a
I mean,
different
yeah,
basis.
it's weird for me to think about testing for a value which is outside of the blocks.
You can't really test it. Yeah, that's the point.
Because it's not a quantum state. Yeah, that's
Yeah.
you do, yeah.
But is
you can
that
test
what's happening there?
It's the same
I
thing
mean,
as what we talked about with the simplex on the coins. When you it's the same non-realistic quantum state. It doesn't
It's
exist.
not
It's a
physical. It's like
well, I mean,
every point
it's
outside of the block sphere, but inside of tetrahedron is just non-physical state.
okay.
Right? It doesn't exist. It's just we have imagine that we have some special constraint in our universe that only allows the qubit be in this particular having this particular distribution if you would test it using those 4 particular tests.
Like mathematically, you can put the numbers in that will paint this picture, but it's not physical. It's a non-physical result.
Yeah, and there's a good reason because why is it not? It's like roughly speaking, it's because you want to rotate this sphere, right? You want to, if you given some state, usually what you do in quantum computation, you rotate it, and you don't want to for your probability vector to go outside of the tetrahedron. So if your physical state, your qubit was actually there, and you perform some quantum computation, it would be outside of the tetrahedron. And now it's not even a valid probability distribution in that using those particular tests, right? So that's why it's kind of a natural constraint to have a sphere inside of it, so that we can rotate it naturally. That's what happened. Yeah. But anyway, there's like besides this tetrahedron state, of course, you can choose arbitrary bases, which you can because you can rotate the tetrahedron itself, right? It's not like the orientation of it doesn't fix. And there's like those there's another one though because they called Q, those special points that are shown there because they call them Q, they correspond to this special basis called cubism. It's just related to quantum Bayesianism. It's just another basis. Don't think too hard about it. But it's like it presents also the same kind of thing. It does the same thing. It projects a quantum state to probability space. Again, the uniform mix also the uniform one, but any other state maybe have different numbers because it's a different basis, but it's again a probability space. Right? We just rotated the tetrahedron around, so it's just a different orientation, right? But it's a more natural orientation because now those Qs are corresponding to those red points, right? So it's essentially what we're asking. But now we can describe it more exactly by some measurement. I was kind of already trying to explain what those tests are, because when you want to describe your qubit using probabilities, you have to come up with some tests, with some measurements. And there's to any basis in this, to any this probabilistic basis, you have a corresponding measurement operator. And in this case, it's called this one. If you want the tetrahedron one, that's going to be this test, right?
What is that?
Actually,
You said it's called that one, but what is that one actually called? What there's like 7.
well, yeah, that's it says like symmetric, informationally complete, positive operator value measurement, something like that. Right. So it's the most important one is because it's a measurement, and maybe in that it's informationally complete. Right. Information complete essentially says that if you measure the state, because this is just operator, and you can measure it, get the probabilities out, you get the quantum measurement object. But if you just want the probabilities, it's essentially the same probabilities that we get when you just we're converting it to the basis, right? So the phase transform, whatever it was doing, it was actually doing effectively some measurement. So we performed some tests, and those are the probabilities, right? So it's kind of natural. If you measure, use the different set of tests, you measure the same quantum state with the different probabilities, and those would be, and to each of those measurement operators, there's a corresponding basis. So that's why we have 2 different ways of converting back and forth. So essentially those, but from the quantum measurement operators, you can extract the corresponding elements because tests in the quantum computational sense are just another states, right? If you just look at the block sphere, what is actual measurement constitutes? In this case, it's like if you're given some arrow, like maybe pointing to 0 or 1, testing it with some other state is just projecting it to some other arrow, right? So it's just you can represent any other test is just with another arrow. So it's also you can represent it by a quantum state, right? And you can extract it from the quantum measurement operator using like these elements, those complicated 4 letters, positive operator value measurement elements. Those can be turned into quantum states. Those are just density matrices. And if you take those quantum states and do the block plot for each of them, they may be not normalized, if I remember correctly. Yeah, those are just pointing to those exact red spheres in our quantum union, right? So those are just showing what are the actual tests to get the qubit as a probability point, probability vector.
Okay,
So
so
that's
just to recap a little bit, so you're talking about the red and blue balls right now,
just
which
red now, just red for now. So this red
just red.
ones, they're kind of already shaped as a tetrahedron, as you can see, right? Those are if you put those layer back, those
Okay,
actually
the points
pointing
of
to
the
those
tip.
exact same. Yeah. So so those are actually the tests I was talking about. Just project as a block sphere exactly to those points. So essentially, if you just take the measurement, extract those elements as a state, those would be exactly the quantum states that constitute that measurement tests. Right? So that's why they're in the same tetrahedral shape that points to the corresponding vertices. And cyan spheres, those are, as you can guess, they in the center of each of those faces, there's some kind of dual to this red one. As a basis is exactly what we call the inverse basis. Oh, I'm not going to show it even. You can inverse it. It's like you can inverse each of those qubits. The inversion in this case means actually a very simple thing. It's just the mirror in the y-axis, if you can see it. Like the y-axis exactly going from here from this point to here, right between this. So you can see that this three.
Okay, yeah.
So this Q3 mirrors to this Q3 star, and every other state is just the mirror image from in this particular plane.
Okay.
Yeah, and when you just and in a way this is like an inverse basis. It can also serve as a test, but it's a very special case inverse. It's just because inversion or conjugate, it also corresponds to a conjugation. Because when you do the conjugation, complex conjugation, it's just putting the minus sign before the imaginary component, right? That's what complex conjugation means. And why the complex conjugation corresponds to the smearing in this plane is because the only well, mathematically, because that's the Y Pauli matrix is the only one that contains the imaginary components. So if you conjugate your quantum state, you're just flipping in this particular plane, orthogonal to the y-axis. So that's kind of geometrically what it means. So if you conjugate those bases, you get just the mirrored version. And together with those, so together with this original red tetrahedron and the cyan tetrahedron, you just get this cube. Right.
Okay. Do we have enough time to get through all the rest of the layers in the next 10 minutes, or?
You know, we can try. There's also if you haven't asked me, I was hoping it.
There's also the potato chip.
I was waiting for that to be the finale.
Yeah, it was a teaser. It's like a hidden secret layer, right? Okay, so all right, so let's go to that last octahedron one, right? And well, that's very simple because you can see that by the labels, from the labels, that those corresponds to some kind of measurement in a particular axis, right? So it's like spin up, spin down in one particular axis of measurement that you choose. So if you choose your z-axis, those are some points corresponding to that projective measurement. So in a way, what happens if you think of this in terms of probabilities, what happens when you do the measurement, right? You started from this. If your qubit lives in a 4-dimensional probability space inside of that tetrahedron here, when you do the measurement, it lives in this 1-dimensional, because it's now just either up or down, right? Depending on which basis you choose. So now it lives on a 1-dimensional simplex. And this is exactly this green lines and the corresponding points, the extremal points, is
I don't
showing
think I see
exactly
the
that.
green anymore.
Hmm?
Do you want to swap back? I don't see
I did
the.
swap back. Well, maybe. Okay.
Can you see
It's
it, Dugan? Oh,
There's nothing green. Oh,
lagging.
there we go. Okay.
uh,
I
Can
guess
see.
it was lagging a little bit.
Mm.
But yeah, those green axes are those 1-dimensional simplices corresponding to this measurement of the chosen basis. So we have a natural choice of basis. We have the x, y, z axis, right? And if you chose those as a basis, then the probability vector in 4D projects to this line, which is a 1-dimensional probability space. So that's how it.
now, is there a reason that the green points aren't on the sphere?
They touch in the edges of the testing cube that was there in the previous.
Well, there was a cube with its vertices on the sphere, and then the cube's facet centroids, space centroids form as a dual construction. The
an
tetrahedron.
internal.
But I mean, it doesn't.
Is it a dual or is it no? Right.
What do you mean dual?
Well, yeah, the cube and the octahedron are dual polytopes to each other. But it's not always the case that the geometric dual to a polytope has the duals having vertices being the actual facet centroid thing. Anyway, this is a different discussion. But I mean, so the green octahedron is
by dual. I think it's like if you invert, there's a
there's an inversion.
Yeah,
like a spherical.
I think inversion as a dual actually turns octahedron to a sphere. I think.
What?
Or maybe.
No, and then not a polytope inversion. There's a very specific operation on convex polytopes.
Okay.
Inverting from a point interior to it in any case.
But anyway, there's a geometric motivation that those green points lie on the cube, but also there's some algebraic motivation because when you do the projection, like if you actually take the quantum state and project it using the measurement, in a way, in some sense, you can say, for example, if you measure in the z direction, right, your quantum states actually is equivalent to taking the average of those red points. So you don't have time to like go into the detail, but if you take the average, they're not gonna end up in this particular north pole, right? And they're gonna end up here. So that's why it's more algebraically. It's also nicer to have like represented like this, right? You still have to a little bit expand it. It doesn't matter in terms of this 1-dimensional probability simplex, but you still it's just more appealing to have it this way. I don't know.
Okay, so I've got a quick question. So which of these layers represents the possibility of quantum states versus the collapse of it not being quantum anymore? Is there like a pure probability space that is represented by one of these blue or green?
Well, the fact that you collapse it doesn't make it less quantum, right? It's like because you can represent classical probability if you're using qubits too.
It's more the basis that determines whether it's going to be quantum or not, because there's a certain line through it, which if all of your probabilities exist on that line, then you won't notice any quantum effects, maybe something like that, or plane rather.
Well, the fact that it's inside the sphere, the fact that you mix the state essentially means that some information left out left the system, right? And that's what happens when you measure. You like given a state, you project it on some axis. Now it's in the bulk of the sphere. Now it's like not radius 1 anymore, right? If you keep rotating it, performing some quantum operations, it still keeps the same size. If you project it again, it can only decrease in size, right? Because you project it on any other axis, it can never grow. So the information can only leave the system when you perform measurement of the same qubit.
So it's a projection. Okay, so every measurement could be considered a type of projection onto a.
Yeah, that's what they call projective measurement. You can either the different types of measurement. There's a projective one when you fix the axis, choose the axis, right? That's what it's why is it called a projection? You project to the axis, or you can generally just pick an arbitrary number of tests, as in that tetrahedron case. You just pick 4 tests and measuring those using those particular states.
Very cool. Okay, time for the Easter egg. We need to finish the stream.
So
Unfortunately,
the
a little
Easter
bit
check
early
is
today.
it's not like well, I would love to explain what it is. But this is like an extra. Let me remove all other layers. So it's like there's a different type of geometric object that one can construct using those probability spaces and in the qubit, which is like looks like exactly as a potato chip, right? But it has a mathematical representation, right? What it represents, briefly speaking, if you think of it, again, I already explained that you can turn quantum state into a probability vector, and it's always going to be a square of the original dimension. So if you have a qubit, it's 2-dimensional with complex amplitudes. Now it's 4-dimensional, 2 squared in the probability space, right? So if it was a 3-dimensional quantum state, now the probability space would be 9-dimensional and so on, right? 4, 16, 5, 25. So it is natural in the probability space to actually think of it as a pair, because you can square it. Now it's probability space of size 4 can be seen as 2 coins, right? two-dimensional probability vectors, because you multiply them together. So it's like a joint probability of 2 probabilities, 2 random variables, right? So that's essentially.
Why is it wavy like that? Why is it?
But that's what you get. Well, that's what you get when you constrained, when you just ask a simple question. Okay, given that you have a probability vectors, and you think of them as actual pairs of 2-dimensional probability vectors, right? As a joint distribution of 2 variables, 2 random binary variables. You can ask a question: what would be the probabilities? What would be the probabilities vectors when those 2 random variables are independent? Okay.
Oh.
That's the simple question. It's like, okay, what would be the points in that probability space that would show to those points as a 2 random binary variables that are independent, so that you can separate them out? It's like just throwing two coins, so just representing as a joint random distribution of 4 outcomes. You present it as a outcomes of 2 random coins, and this potato chip is essentially the space of those probability vectors that can be represented as this separated case of binary variables. So it's kind of looks nice.
Very cool. Okay, that's going to be my new emoji for the Discord server. Okay, thanks guys. It's a short and sweet one for today. We'll catch you in the next one. Bye for now.
Good work, Nick.
Bye everyone.